Hello everyone, welcome back. So last time we were really focusing on the translational motion of a body, and even though we talked about just a little bit rotational motion, we didn't do anything with that. So this time we're actually going to start dealing with rotational motion. So we're going to analyze the planar kinetics of a rigid body undergoing rotational motion. So why do we care? Well, first off, the crank on the oil pump rig, it undergoes rotation about a fixed axis. This axis right here. And it's caused by the driving torque M from a motor. Now, as the crank turns, a dynamic reaction is produced at the pin. This reaction is a function of angular velocity, angular acceleration, and the orientation of the crank. Now, if that motor exerts a constant torque M on the crank, does the crank turn at a constant angular velocity? And would that be desirable for such a machine? Well, if it's an oil pump rig, you probably don't want it just like accelerating over and over again until it's going super, super fast. I mean, maybe that's pumping oil quickly, but I'm more likely to think that you're wasting oil. So let's avoid that. Another thing is this is a Sharpie impact machine. It's used to understand how materials, which are usually rectangular, are affected by like super cold temperatures or being stretched, or by having a little chip in it and seeing, okay, if I change the temperature, does it take less energy to break it? If I stretch it, does it take less energy to break it? If it got a little chip in it, does it take less energy to break it? And so you can understand more about it from that. Now, it's released from rest when theta is equal to 0. So when it's right up here. As it falls, its angular velocity is going to increase. Do you think you could determine the angular velocity when it's in that vertical position? Well, I hope so, because it's going to be 0 to begin with. And on which property of the pendulum does the angular acceleration depend? What do you think? I'm guessing it's going to be on the mass moment of inertia, but I'm just your teacher. What do I know? And then you're going to try to figure out what is the relationship between P and the angular acceleration. Okay, so let's jump right into this. So we showed this last time that a rigid body, it can be undergoing rotation. And if it's by itself, then it's going to rotate around the centroid. However, in this case, we're rotating about a fixed axis. And so it's not quite the same. So what we're going to see is that we're going to have a tangential component of our acceleration, which is going to be related to our angular acceleration, and a normal component, which is related to our angular velocity. Or that this comes from the whole v squared over r thing. We can actually show how those are related if you want, though we've done that in the past. Now, since the body experiences an angular acceleration, its inertia creates a moment which is equal to this, the mass moment of inertia times the angular acceleration. And that's going to be equal to the moment of external forces acting about point G. So we have three scalar equations of motion, and they look like this. So this one is no longer 0. It was before for just translation, but no longer. Now, if we want to, we can replace that sum of the moments around point G with the sum of the moments around an arbitrary point. And so in that case, we're going to have our regular moment of inertia right here, our regular moment right here. And then along with that, we're going to have these other components. So we're going to have the distance to the centroid times that tangential component of the force at the centroid. And then if we simplify things, what we get is, okay, well, this was a component, or this was a was proportional to my angular acceleration. So if I rewrite that, I can get it as one nice equation, which has something very, very like the parallel axis theorem. Like right here, this is the parallel axis theorem just acting on it, and it's all multiplied by the angular acceleration. So it's pretty nice. The overall mass moment of inertia times the angular acceleration. And so we can then rewrite that, just remembering that this is equal to the mass moment of inertia around the centroid plus that correction term from the parallel axis theorem. We have our three equations of motion. So how do we solve these kind of problems? Well, it's not too difficult. First, get an inertial coordinate system and specify your direction for normal and tangential components. Then draw a free body diagram. Make sure you get all the external forces in there, including the weight. Don't forget the weight. Don't forget friction if there's friction in these problems. Whatever there is, make sure you have included it. Figure out what the maximum of inertia is around the centroid, around some arbitrary point. And then write the 3 equations of motion and identify the unknowns. We'll solve. So not too bad. So one last thing is, if you don't know, if there's not enough from this, then you're going to have to use kinematics. Remember, we never escape kinematics. They're going to be there until the very end of the semester, and you're probably going to need them even on those final few assessments. So that'll be it for this time. Next time we'll jump into an example. So thank you for listening, and I'll see you all later. Have a great day. Bye-bye.